Okay, so this is the lecture for static distributed loads. Okay, so we will see how we can replace a distributed load by just one resultant forces at the right location. Okay, so we need to compensate for the moment created by the forces. Um, so we have, and we will just do 2D. Okay, so we have a distributed load, okay, like this. Oops. And this distributed load is made of a lot of little force that apply. Let's say it's a beam there. Okay, let's say we have a beam there. Okay, it's apply on the beam. Remove it, but we have a beam. Okay, so we have a lot of little forces. Because that's little forces, we call that all those little arrow, we call that dF. Okay, a dF, it's not just a line. Okay, it's not possible to be just a line. Okay, it has to be a surface. So we can draw a little dF as it is a little rectangle. Okay, so let's use this one, this little dF. Okay, we will use it, but that's a little rectangle. So we split, we cut the force that is applied on the beam on little rectangle, little force made of little rectangle. Okay, they are so little that the width is called the x. Okay, we are on the x-axis and this is the y-axis. So the width of this rectangle is dx. I forget to say that we know, something that we know is the function of the distributed load. So let's call it wx. Okay, so we know that this function. So the 8, let me do it in green so you can see something. The 8 of this rectangle is W. Okay, let me try to remove this one. Oh, I can't. Okay, that's fine. Oops, W. This one is W. Okay, so the dF it's equal to W. Okay, and that's W of x time dx. Okay, so your little dF, it's a little rectangle with 8 of W at this time, and we are exactly, this is x. Okay, there's a multitude of little dx. So for example, we can take this df there, this little rectangle df, that will still be dx. Now the x is this one, and the 8 is this one, but it's still w of x. We change x, but that's another df. Okay, and we have a lot of little df everywhere on this beam. So if we want to know the force, the resultant force, we need to add all those df together. And when we add them together, what we have is we have the area. Let me make it in light like this. We have this area there. Okay, so this area in blue, it's FR. So it's also equal to the area, the blue area, and it's equal to the sum of all the little df. Okay, so when it's something that is big, we write the sum like this. So for example, sum of the force. Remember, we did FR, it's equal to F1 plus F2 plus F3 in the previous sections. Here, F1, F2, F3 is very small. So we don't do a sum, we do an integral. Okay, so we will do the integral of all the little df. Okay, and now the df is equal to, so FR equal to the integral of what? Of wx dx. The question when we have an integral is always what are the limits of the integrals? And the limits depends always to the little element of integrations. Okay, the little, so that's about dx. So we need to write some limits for dx. So it's between the beginning of the load, let's call that x1, the end of the load x2. So it will be from x1 to x2. Okay, you can see it written also fr, it's equal to the integral on the length of the load of wx dx. Okay, so L here it's x2 minus x1. Okay, I will use L because it makes the explanation a little bit easier. Okay, so we found the formula for fr, that this formula. Okay, but remember, when we want to replace a system of forces or a distributed load, okay, we want to know what is the resultant force, but also what is its location. So we want to replace this distributed load by one. Let me make it bigger. Okay, I will draw in light green the previous load, so that this one, okay, oops, like this. So that's my distributed load. At the same W of x, okay, it's light gray, because what I want on this side, it's FR, okay, and I want to find the distance of FR from, let's say, from this point, from 0. That's called x bar, okay, like the mean of the average, right? That's the same thing. Okay, so, and those two systems are equivalent. Okay, so on the left, we have the distributed load. On the right, we have just one resultant force is left. And we have its locations from, let's say that's from the origin O. But the question is, how do we find x bar? How do we find x bar? We will use the exact same steps that we did in the previous sections. We will use the moment. So we will say that the moment of on the left is the moment of all the little df, so that the sum of all the moments df, let's put this the integral. Okay, so if we add all the moments done by the little df about the point O, it should be equal to the moments done by the resultant forces about the point O. Why? Because it's equivalent system. Okay, the difference from the previous session is, instead of having sum of the moment of, F1, the moment of F2, the moment of F3, we have an integral because it's little element of forces. So, what I am doing, here we go. Okay, and let's try to keep everything for this one. Okay, so the moment of DFO. So let's come back on this little rectangle there. What is the moment created by this little df about the point O? So that's the distance x. So the moment m df about O, it's equal to what? The force df times x times df, right? X, that the distance, and df, that the force. That's the same thing that say that the moment is equal to d times f. Same thing. But x is the distance, okay? Because right now this little element of forces is at a distance x from O. So that's for the left, okay? And on the right, the moment created by the force Fr is the distance, x bar. And let me write it red because we don't know it, okay, right? That's what we are looking for. Okay, that's our unknown. X bar times the force Fr, the resultant forces. Okay, so let's write better on the left. So that the integral of x df is wx dx. Okay, and the integral there, it's the little element is dx, so it's about L, because x is going from x1 to x2, but it's like saying that is on the length of the distributed load. And on the right, it's x bar that we are looking for, and Fr, we found that this the integral about L of wx dx. Okay, what our unknown is x bar. So remember, that's what we want to write. So we can write that x bar is equal to huge fraction line, this one, the integral about L of x times W of x dx, and divided by L W of x dx. And we can square this formula. Okay, so what we found is we found the formula. We found two things: the formula for FR and the formula for the location of FR. So if we want to replace a distributed load, we will use those two formula. And it's in integrals. It works for any distributed load. Okay, any shape. It could be a load crazy like this, could be a load like this, a load like this, a load like this. Any shape, I don't know, shape like this. It could be above the x-axis or below the x-axis. Okay, as soon as you use the right function W of x. Okay. So that's the first part of the lecture with the explanation of the integrals. I will do in the next video the explanation of usual distributed load, and I mean rectangle and triangle distributed load. See you in the next video.